Okay, hi everyone. Welcome to the Topos Institute Colloquium. Today we are pleased and honored to have André Joyal from the University of Quebec in Montreal. And today he'll be speaking to us about the free completion of categories. So André, whenever you're ready.
Thank you very much. Yes, I wrote part one because I will be happy to give another talk sometime later. But this is just a talk to give you an idea of the kind of maybe technology that I have developed on this subject. And uh, so. Yeah, it's all inspired by Whitman theory of three lattices. Uh, it's kind of an amazing thing that it can be extended to lattices over enriched over a quantale, and also to bicomplete categories, and even to bicomplete enriched categories. So this theory of Whitman is kind of very stable, or it can be generalized all the way from lattices to categories and even to infinity categories. So, in that sense, it seems to be a fundamental aspect of category theory. Uh, and it seems to have also applications to the semantic of linear logic. In my work with Hongde Hu, this is almost like 25 years ago. And I want to apologize to everyone I had promised to give a draft of my work on bicompletion during the last 25 years. So that's many people. And I am presently writing the draft, and I hope to finish it this spring, maybe before. So you are welcome to keep asking me about the draft so that to make sure that I will actually complete it this spring. So my goal here is to introduce the few basic ideas of the theory of three bicomplete categories. So my plan at the moment for this talk is to recall Whitman theory of three lattices and then introduce the three bicomplete categories and some of the basic notions there, uh, like the exact co-exact factorization, and then the rigid model structures, Quillen model structure, which is a very special kind, which I call rigid. Okay, so Whitman theory of three lattices. A lattice L is a poset with binary infima and binary suprema. There are many variations of what a lattice can be. For example, it could be a bounded lattice, which means that it has a maximum element and a minimum element. So I just, for this introduction, this first page, recall the notions of a lattice, classical notions of a lattice, where you have two operations, the infimum and the supremum operation. And this structure is algebraic. It's completely given by a relation between these two operations. So you have the associativity of the infimum operations and the supremum operations, and commutativity, idempotency, and also the absorption for the connection between the two operations. And free lattices because they have special properties. Of course, free structures have special properties. So, for example, the free monoid on a set is special because, for example, it has a cancellation property among other properties. And free lattices have also. And the main property that a free lattice has is this first was described in the first line here, is that if an infimum, the infimum of x and y is smaller or equal than the supremum of let's say of u and v, then uh, one of four things is true. It could be because the infimum of x and y is smaller than u, or because the infimum of x and y is smaller than v, or uh, that x is smaller or equal to the supremum of u and v, or y is smaller or equal to the supremum of u and v. Of course, if any one of these four conditions is true, then surely the infimum of x and y is smaller or equal than the supremum of u and v. But the remarkable thing is that the converse is true, is that the only reason for an infimum of x and y to be smaller or equal than u and v is that one of these four conditions is true. I mean, somehow you could say that one these are the four trivial reasons, I would say, for the infimum of x and y to be smaller or equal to u and v. And so you could say that if the infimum of x and y is smaller or equal than the supremum of u and v, then it must be for a trivial reason. It's one of the four trivial reasons there. So it's kind of strange that this could be true because there are somehow very few examples of free lattices. In nature, a lattice could be distributive, for example, or maybe it is a modular lattice, etc. But in natures, I would say that lattices are never free. I mean, Whitman was really amazing to discover that free lattices have this property because you never observe free lattices in nature. Of course, one way to observe one is to construct one, but in order to construct it, you actually need that property of discovered by Whitman. In addition to, I call this property, I needed a name. This property is very important in the theory of free uh, bicomplete categories, and I call that softness. Hmm. I don't really know why I choose that name. So I say that lattice is soft if this first condition discovered by Whitman is true. You could say that this is a Whitman lattice, maybe, but I call it soft. Uh, Now, in addition to the softness conditions, you also have other conditions for the lattice to be free, and these other conditions are kind of obvious. It's about the generators. So the elements of the poset P are generating this lattice, and their image in the free lattice are, I would say, atomic elements or irreducible elements. So the second condition is saying that the generator of this free lattice is sup irreducible because if IA is smaller than the supremum of U and V, then it must be because IA is smaller than M. And also they are the they are infima irreducible. Uh, and the last condition is obvious, just saying that the map I is preserving, of course, preserving, but also conversely, if IA is smaller or equal to I of B, then A must be equal to B. Okay. So these are necessary and the sufficient conditions for a lattice to be free. Now, Whitman himself extended his theory of free lattice to lattices that are alpha complete, where alpha is some regular cardinal. So uh, I recall the definitions of an alpha complete lattice. It means that every subset of the lattice of cardinality smaller than alpha has a supremum and also an infimum. And the category of alpha complete lattices is also algebraic in some infinitary sense if you have these infinitary operations of suprema and infima. And the forgetful functor from the category of alpha complete lattices, where the maps there are preserving uh, alpha suprema and alpha infima, then the forgetful functor to poset has a left adjoint, taking a poset to the alpha complete lattice freely generated by P. And you can introduce the notions of alpha and decomposable elements uh, if that's the conditions 1 and 2. So an element of the lattice is alpha and decomposable if it is, I would say, suprema irreducible with respect to the alpha suprema, and also infima irreducible with respect to the infima of subset of cardinality smaller than alpha. And Whitman has this theorem that the inclusion of a poset P in the alpha complete lattice generated by P is an isomorphism between the poset P and the poset of alpha and the composable elements of alpha P. But there is more about the free alpha complete lattice. So let me say that an alpha complete lattice is alpha soft if the following implications hold: that if you have the infimum of a subset S of causality smaller than alpha, if an infimum is smaller or equal than a supremum for another subset of causality smaller than alpha, then it must be for a trivial reason. And the trivial reason means that actually this supremum is larger or equal than an element of S, or the other way around, that the infimum of S is smaller or equal than an element of T. So this is a condition on an alpha complete lattice, which when it is true, I say that this alpha complete lattice is alpha soft. And then the theorem of Whitman is that an alpha complete lattice L is free if and only if it is alpha soft and generated by its alpha and decomposable elements. And we would like to generalize this to categories. So we have to generalize two things. First, the softness conditions and the composable elements conditions. So let's start with the easiest, which is about alpha and the composable elements. So first, I recall the notions of a complete and co-complete and bicomplete categories. So this is pretty standard. A category is said to be complete if every diagram has a limit. And by a diagram, I mean a small diagram. I mean a diagram D indexed by a small category I. Well, actually, I will essentially exclusively consider locally small categories. A category is locally small when the offset between two objects is a set, is a small set, if you like. If you are working with the universe, then you want to say that a category is locally small if the offset between any two objects is a small set. And so there's a notion of a locally small uh, com complete category. An example is the category of set. The category of set is locally small. It is complete and co-complete. And co-complete means that every diagram has a co-limit. Uh, and and then there is a notion of a bicomplete. Category is bicomplete if it is both complete and co-complete. Now, there are corresponding notions of continuous functor. A functor is continuous between complete categories if it preserves limits, and co-continuous if it preserves co-limits. And then I say that the functor between bicomplete categories is bicontinuous if it is both continuous and co-continuous. Okay, so now I introduce a notation. Every locally small category K admits a free co-completion. And I introduce a notation. I write sigma K for the free co-completions of K, because sigma is often taken as a notation, at least in logic, for suprema or maybe existential quantifiers, things of this sort. And the functors between K and the free co-completions, I write it also sigma. And there is also a free completion, which I write pi of K, and the functors is also denoted small pi. And I comes to the free bicompletions, which I write lambda with lambda K. Now, it's very simple to verify that the three co-completions exist because it's given by the pre-sheaf category on K when K is small. We come to that at the moment, so there is no problem with that. The free completion is also very easy because this is the dual. The free completions of K is actually the opposite of the free co-completions of K off. So it's no problem with that. It is harder to see that the free bicompletion of locally small category exists and is locally small also. That's a bit surprising, but we will come to that in my talk. Okay, I discuss very quickly here the constructions of the free co-completion of a category and its precise definition. So the definition is about the fact that any functor from K to a co-complete category E can be extended uniquely in some sense, to the free co-completion. Actually, there is an equivalence between the category of functors from K to E and the category of co-continuous functor from sigma K to E. So I write fun Ke for the category of functors from K to E, and I write fun exponent Cc for the category of co-continuous functor from sigma K to E. And you have this functor sigma, small sigma, from K to sigma K, and composing with sigma, or pulling back along sigma, becomes an equivalence of categories. Okay. So there is a formal definitions of what this sigma K should be. And when K is a small category, sigma K is the precede category on K up. This is a very standard uh, result of category theory. And it is easy to prove, but it's a kind of miracle. Look, there is a concrete description of the free co-completion of a small category. It's there, it's free, it's given to us. It's given to us by who? I don't know. Well, maybe the first to realize that could have been maybe Grothendieck, maybe. I don't know exactly who. I would be curious actually to know who first realized that the category of species on the category of small category K is the three co-completions of K, and that the functor sigma is the unit functor from K to the, okay. That's so simple. That's so amazing. That makes life so easy for category theorists and mathematicians that the free co-completion is there. And now it turns out that when K is locally small, the free co-completion sigma K is the category of presentable precede on K up. So it's a very small extension of the category of precede. So a contravariant functor from K to set is said to be presentable if it is a small co-limit of presentable, of representable functor. So we know what a representable functor is. Now, if you take the small co-limit of representable, so the co-limit actually of a diagram of representable indexed by a small category, you get a presentable precede. And sigma K is exactly the category of presentable precedes. And it's very easy to study, right? It works very nicely. Okay, I recall the notions of sigma atomic object. On a co-complete category, I will say that an object is sigma atomic if the covariant functor defined by A is co-continuous. This covariant functor defined by A is actually continuous by almost definition of what the limit is. So this functor is always continuous. So when the functor is co-continuous, then we say that this object is atomic, sigma atomic, because it's about the co-continuity of this covariant functor. There is a notion of pi atomic that I will describe in a moment, but uh, now it's very easy to check that the retract of a sigma atomic object is sigma atomic, and also that the functor sigma, the unit of functor from K to sigma K, it takes an object in K to a sigma atomic object. And actually, every sigma atomic object in sigma K is a retract of a representable. So, and then it's not difficult. This is a standard theorem of category theory that a co-complete category is free if and only if it is generated under Coulomb by sigma atomic object. So typically, the category of pre-sheaves on the small category K is free, of course, and it is generated by representable, and all representable are sigma atomic. There are more sigma atomics than the representable. Actually, the retract of sigma of representables are also sigma. So you could, if you want, you could add all the retract of representable, and you get what is called the Karubi completion of a category. This you close the category on the retract, and then if you do that, then the representables are exactly coincide with the sigma atomic pre-sheaves. Okay. Now there's a dual construction for the free completion, and there's a notion of a pi atomic object. So I go quickly about that because you just dualize everything. So when K is a small category, pi of K, the free completions of K, is the opposite of the category of covariant functor from K to set. And you have the pi atomic object and the dual theorem that a complete category is free if it and only if it is generated under limits by pi atomic objects. Now, the definitions of pi atomic is dual to sigma atomic. An object is pi atomic if the pre-sheaf defined by A is actually taking, which is a contravariant functor, is taking a product, or I would say limit in general, into colimits. Okay. Now, a little remark here on completely distributive categories. Completely distributive categories were studied by many people's category theorists. You have a paper by Day and Lack. So the remark is, the crucial remark is that if you take the co-completions of a category, C, then this category is already complete. You just co-completed it, but it will be complete if C is complete. Well, it's also complete in other situations. For example, if C is small, this is the pre-sheaf category and sigma C is complete. But in general, if you have a locally small category which is complete, then the category sigma C is also complete. And therefore, you have the co-limit functor from sigma C to C, because if C uh, is bicomplete, assuming that C is bicomplete, there is a co-limit functor from sigma C to C. And the definitions of a completely distributive category is precisely that this co-limit functor preserve limits. It's a bit surprising. The co-limit functor preserve limits. Okay, so there are examples of that. So of a completely distributive category. It's a bicomplete category having the property that the co-limit functor from sigma C to C is actually preserving limits. So, and actually, there are many examples because if you take any small category K, if you want, if you, for example, then pi sigma pi K is completely distributive. So actually, the notions of a completely distributive category is kind of algebraic, and this is the theorem of Marmot, Lejo, Roseborough, and Wood. And it is a situation where I would say that where the product is distributive over sum. You see, in lattice theory, we could define what is a completely distributive lattice. It is a situation where the infimum is in some way distributive over the suprema. And this situation do exist in category theory, and this is called completely distributive in category theory. So this is just a little observation that, of course, in lattice theory, distributive lattices are very important. Completely distributive lattices are less known, but they are also important. And in category theory, there is also a notion of completely distributive categories, which has not been studied that much, but I believe it is quite important. It's a situation where the infimum is, or the product is distributive over the coproduct. And of course, in topo theory, this is also the case that colimits are distributive over finite limits, right? For in topo theory, this is essentially what topos is. It's a bicomplete categories where colimits, where finite limit distributive over arbitrary colimits. Okay, but now we are going to move into a completely unknown territory where there is no distributivity between of limits over colimits. It's completely unknown. It's a very strange place, but it's precisely the free bicompletion. So I return to the definitions of what the free bicompletion is. So the free bicompletions, which I write lambda here is just a letter. I mean, I think I took it because of lattices, three lattices. So we could use another letter. So there was sigma, pi, and now I use lambda. So the category lambda k is bicomplete, and it is free on k because the functor lambda upper star is an equivalence of category. On one end, you have the category of all functors from K to E, where E is an A bicomplete category. And on the other end, you have the category of bicontinuous functor. This is the BC here in exponent. Bicontinuous functors preserving both limits and colimits from lambda K to E. And there is an equivalence of categories between the two. Okay, that's the definition. But given a bicomplete category, we can say that an object is atomic if it is both sigma and pi atomic. Okay, now I come to the theorem of generalized Whitman theorem that a bicomplete category is free if it only if it is soft. I will describe it in a moment, and generated under limits and colimits by atomic objects. But I need to explain what a soft category is. So first, I will define what is a soft functors of two variables. So if you have three bicomplete or co-complete categories, you just need co-complete categories to define what the soft functor is. The functors of two variables, f from C cross D to E is soft if the following square of canonical maps is a push-out for every pair of diagrams A and B. Now, if you have to pay attention to to realize that there is a canonical square of maps like this if you have a functor between co-complete categories. What the square does is to express the object in the lower right corner, which is called F colimit A and colimit B, as the colimit of two of three objects, three other objects that can be computed from the diagrams A and B. So this is not a square that we meet often. Actually, in it's I think it's not in the literature. The square is very easy to write down, but it's never there in the literature for strange reason. I mean, so it's not in the literature, and nobody is asking for the square to be a push out. It's never not in the literature, but it's there. It's very easy to write. You okay? So I say that the functor f is soft if the square of canonical map is a push out for every diagram. Okay, that's a definition. Okay, now we can use it now to say that a bicomplete category is soft because you have the Hahn functor, which is the functors of two variables from C up cross C to set. And if the category C is bicomplete, then the three categories there involved are co-complete. Of course, set is co-complete. C is co-complete because C is bicomplete. And C up is co-complete because C is bicomplete. Okay. Okay, now we can put the conditions on the Hahn functor and ask the Hahn functor to be soft as a covariant functor from C up cross C to set. Okay. Now we take a pair of diagrams, A and B, from with values in C. Now the diagrams A from I to C is producing a diagram from I up to C up. You just take the opposite functor. Okay. So we can translate the conditions of softness for the covariant functor F as conditions of softness for the functors on as a contravariant functors on C. And you get this diagram, you get the diagram. And beware that in this diagram, all the colimits outside hum or limits they are all colimits. It's a diagram, it's a colimit diagram. You do have limits in this diagram, but they are all inside the hum. And what it says is that if you have a map from a limit to a colimit, okay? So this, I'm looking at the lower right corner of the square. And what it says that if you have a map from a limit to a colimit, then this map can be described in two ways. Possibly you can lift it up because it's a push out, you know. If you have a push out, the two maps generating the push out are collectively subjective. It's always the case. If you have a push out, you have two maps, I would say conical maps that land into the push out, and these two maps are always subjective by constructions of a push out. So the fact that this square is a push out implies that if you have a map from a limit to a colimit, are there two things. It could be lifted up, which means that it can be explained. This map would be a map from some AI to the colimit of B. Remember that A is a diagram, and I is an object of the indexing uh, category of the diagram A. So if you have a map from the limit of A to the colimit of B, you will be able to factor this map, factor, because there is a projection from the limit of A to some AI, where small I is in the limit of I, of capital I. So there is a projection from the limit, projective limit of A to some AI. And these conditions imply that your map from the limit to the colimit will factor to some of the projection. Unless, because maybe it will lift horizontally on the left-hand side, because now on the left-hand side, there is an inclusion from Bj to the colimit of B, okay? And your map either factors through a projection from the limit of A to some AI, or it will factors through the inclusion of some Bj into the colimit of B. Okay, so we recognize now Whitman conditions, either one or the other. Ah, but the fantastic thing is that these two conditions can be put together. There is a situation where maybe your map will factor in both. You see, you could have a map from the limit of A to the colimit of B that factors to a projection to some AI and also some inclusion to the colimit of B. So in this case, your map will lift to the upper left corner of this square. Fine. But not only that, it could be factors in many ways. Maybe it factors to this projections and maybe also to this projections and maybe to this colimit. So there could be many ways. Well, it's all taken care of by the fact that this diagram is a push out. That all the relations that you may have between these possible factorizations are exactly given by the fact that this is a push out. I could not believe it when I realized that maybe this is true. I said maybe I'm asking too much. It can't be true. I mean, this is like a foolish dream that this maybe could be true. Okay, okay, but it is true. It is true. Yeah. Okay. So I would like to tell you an idea how this is proved because it looks like even if this is true, that's going to be very complicated to prove. See, because you have all these relations. I mean, how are we going to manage to prove these relations? You see, so look, it's not that difficult to prove. What you have to do in order to get there is to believe that this might be true, and then you keep thinking about it, and eventually you find an easy proof. So if it is true, it's not because I am that good as a category theorist. The reason I was able to prove it is I managed to believe that it is and kept working on it until I realized that there is a rather easy proof. I will try to give you an aspect of that proof. I will not give you the complete proof because it may become a bit technical, and there is not enough time in this talk. Okay, so first, I introduce this notion of an exact natural transformation between two functors, between two complete categories. So if you have two functors, f and g, between two, and natural transformations u between f and g, where f and g are functors from C to D. I introduce the conditions and I will discuss its meaning in a moment. But the functors may or may not preserve limits. The categories are complete. So if you have a functors between complete categories, it's natural to ask, does it preserve limits or not? Okay. Now, to preserve limits means that if you have a diagram A from I to C, if you have a diagram A from I to C, then there is a comparison map from the value of f at the limit of A and the limit of f of A. Very standard, right? It's the magical things about functors between complete categories. There's always a map from the value of f of the limit of A and the limit of f of A. There's always a map, a canonical map. And this canonical map is so useful because you could say, well, now if you could say, well, now I will say that this functor preserve limits if this map is invertible. So to preserve limits is a property of a function. It's marvelous, right? It's a property. It's not a structure. You have the categories C and D, and the functors preserve limits if this map is invertible. Thanks God. To preserve limits is a property. It's very different from let's say you say a monoidal functor. What is a monoidal functor? Okay, a monoidal functors is a functors equipped with that and that and that and that, satisfying that and that and that. So you have to say it's equipped. To be monoidal is a structure, it's a structure. And this is why the theory of monoidal functors is more complicated than the theory of functor preserving limits because it is a structure. You have to take care of these structures and the coherence conditions, and it's a mess. I mean, it's also very beautiful, but for functor preserving limits, it's a property. Okay. Now, suppose that you have natural transformations from F to G, then you get a little square. The natural formations is a square. And uh, definitions, you could say that the natural transformation is exact if the square is a pullback. It's a very simple notion. It's a property of natural transformation. If it's a pullback for an A diagram. Okay, now an observation that if you take, if G is the terminal functor, the terminal functor from C to D is the constant functor with value the terminal object of D. So C and D are complete categories, and the terminal functor is simply the constant functor with value the terminal object of D. Okay, so there is always a natural transformations from a functor F to the terminal functor. It's canonical, and this natural transformation is exact if and only if the functor F is continuous. Well, it's very easy to check. So if G is the terminal functor, then the exactness condition that I just imposed on these notions of exactness transformation will be very simple because the downward, the bottom map of the square, the bottom horizontal map is another it's an isomorphism in this case because G is constant. Okay, okay? And now if you have a square where the bottom map is invertible, the square is pulled back if and only if the top map is invertible. That's a classical lemma about pullback square. So if the bottom map is invertible, the top map will be invertible too. and therefore the functor f will be continuous. So, in other words, the notions of exact natural transformation is a generalizations of the notion of continuous functor. I would say it's a kind of relative continuity because we may think that f is sitting over g and that f is continuous relative to g. And if g is terminal, then continuous with respect to the terminal, exact with respect to the terminal, means that f is continuous. Now there is a notions of coexactness transformation between two functors. It's just the dual. You reverse everything. You have the same notion. And if bottom is the initial functor from C to D, then the natural formation from bottom to G is coexact, if only if the functor G is co-continuous. Okay. Now, I introduce an extra notion. We are going to consider functors from the lambda k, from the free bicompletions of k, to some category S. Actually, bicomplete category S. In the important examples is the case where S is the category of set. But I introduce here the notions a bit more general. So we are looking at functors from lambda k to some bicomplete category S. Now, since lambda k is equipped with a functor lambda from k to lambda k, lambda k the free bicompletions. Okay, I'm assuming it exists. So we have this functor lambda from k to the bicompletions. And therefore, if I have a natural transformation between two functors from lambda k to s, I call this natural transformation small f, then I can pull back along lambda this natural formation. I can restrict the functors fmg along lambda. So I have lambda upper star of f, which is a functor, which is a natural formation from lambda upper star of capital F to lambda upper star capital G. Okay, so definition, this is, I call this natural formation, so lambda equivalence, if it becomes invertible when you restrict the natural transformation F along lambda. That's a definition. Okay, now is the lemma, which is key for everything. I will not prove the lemma here at the moment. Maybe I could do that in some future talk. I will not prove the lemma. It's not very hard to prove. Okay, it's kind of formal. You use the universal property of lambda k for that. You use some construction, okay, and you prove the universal property. And the here's the lemma is that if you have a natural transformation, let's say from f to g, then it can be factored uniquely as a co-exact lambda equivalence followed by an exact transformation. I will explain why maybe in a moment what this is about. So it's not true that you can factor uniquely as a co-exact natural transformation followed by an exact. You need to impose that the first one is a lambda equivalent. But it's almost like saying that every natural transformation can be factored as a co-exact natural transformation followed by an exact one. But don't forget, You should impose that the first one is a lambda equivalence. Why the first one? No reason. If you want, it's not stated here. You could also have a factorization, unique factorizations, as a co-exact transformation followed by an exact lambda equivalence. I mean, you have to impose that it is the lambda equivalence either on U or on V. Here I choose to impose the conditions to be a lambda equivalence on U because I want to use it in a moment. But that's your choice. The two possibilities are true. Okay. Now I recall what a factorization system is. It's two classes of maps in the categories called a factorization system. I don't mean weak factorization system. I mean factorization system where the factorization is unique up to unique isomorphism. Okay. So this is standard. Okay. Every map factors uniquely as a map in the first class, or maybe it's called the left class, followed by a map in the right class. And this factorization is unique up to unique isomorphism. And then they have these orthogonality properties. Okay. If, okay. Now you maybe guess what I'm coming to. There's a model structure. The lambda equivalences are the class of weak equivalences for model structures on the functors categories we were looking at. The cofibrations are the co-exact natural transformations, and the fibrations are the exact transformation. It's kind of very. I mean, I could not believe it. I mean, the model structure there. I mean, I could not believe it. I mean, when I saw it, you know the story that if you are a hammer, you see nails everywhere. And I am a hammer about model structure because I have been playing with model structures half of my mathematical life. Okay. And so when I realized that was this model structure, I was like, okay, I am making it up. I want to see a model structure everywhere. Okay, so that's it. Okay, so there is a model structure, but the model structure is rigid. Rigid means that the factorization system in the model structures are unique factorization. The usual notions of Quillen model structure, you have a weak factorization. It's very important in the multiple theory that you have weak factorization system. This is an unusual kind of model structure because the factorization is unique. Okay, so if you take an object, you can replace it by a fibrant object, and then take the cofibrant replacement of this fibrant object, or maybe you can do it to it, and you always get to the fibrant cofibrant object. And in the situation of this model structure, remember that it's about the category of functors from lambda k to a bicomplete category S. It's a model structures. The fibrant object are the continuous functors. The cofibrant object are the co-continuous functors. And the bifibrant objects are the bicontinuous. Okay, so I recall I'm almost maybe over. I should maybe wonder if how much time. I think I have spent all my time.
An hour in. But it's up to you, Andre. Up to you.
I will I will try to speed it up. I'm sorry. Uh, okay, so there is notions of fibrant object in a rigid model structure in general, and a Fibonacci replacement. And if you want to get a Fibonacci replacement, you do as the usual. You factor you take your object, you factor the map to the terminal. You take the map from the object A to the terminal, and you factor this map as a trivial cofibration followed by a fibration. And you get the Fibonacci replacement of that object. But in a rigid model structure, this Fibonacci replacement is giving you more than just the Fibonacci replacement. You are actually reflecting your object into the subcategory of Fibonacci object. This replacement is actually functorial, and it's a reflector. You're reflecting the whole model structure in the subcategory of Fibonacci object. And that will be important for what I'm going to say, because it means that if you take an object and you manage to show that you have reflected it, if you reflect an object into the Fibonacci object, then the maps reflecting it, the reflector, the maps from, let's say, if you have a map R from A to B, and which you reflect in the Fibonacci object, then you will know that this map is a trivial cofibration. Because there is an equivalence between reflecting and Fibonacci replacement. And you can prove that a certain map is a trivial cofibration just by reflecting an object. Mm. Okay. Okay. So that's what I write here. If you replace an object F uh, by a continuous functor in a universal manner, the Fibonacci object are the continuous functor. So I write FC for the continuous reflections of a functor F. Then you will know that this natural transformations is co-exact, because the co-exact lambda equivalents are the trivial cofibration. So you will know that it will be co-exact. Okay, now here is an example of a co-exact natural transformation. Well, actually of a reflector. So you take any diagram A, and now you can take the limit of this diagram. You're in lambda k. There's a limit. But you could also take the co-limit of the representable functors that are defined by this diagram. You get a map this way that goes from the co-limit of AX. Now X is some object. X is some fixed object here. And you A into X, you get the diagram in set. It's a diagram in set. And you can take the co-limit of this diagram in set. So that's the domain of the map that I'm constructing. Okay. And this set is very different than just arming the limit into X. You have two things and they are very different. Okay. And this is a natural transformation in X. Just standard category theory here. What am I using? I'm using that lambda k is complete because I want to take a limit. And that's it. I take a diagram in lambda k, and then I construct that. Okay. And I get two functors on lambda k. They are both covariant functors on lambda k. The domain of this map is representable. It's representable by the limit of A. But the co-domain is a co-limit of representable. On one end, you have a representable, and the other is a co-limit of representable. Okay, and you have a map between the two. And this natural transformation, I want to I want to prove is co-exact. Now we need to prove, the proof of that depends on the fact that we are working in lambda k. It will not be true if it's not in lambda k. If it were just from a diagram in some category with finite limits, but the natural formation is good. Now, why is it co-exact? Well, it's co-exact because of the previous lemma, because it is reflecting f into the exact function. So it suffices to show that this map exhibits the best approximations of f by a continuous functor. In other words, if you take a continuous functor g, you want to show that the natural formation, you see, whatever, you just check that it's reflected. It's very standard. It's elementary. There is nothing deep about that. You could the fact that it reflects does not use the fact it's lambda k. It's just C is an A category with limits, and this functors is going to reflect. It's completely elementary. Okay, but the fact that it reflects implies that this map is a co-exact lambda equivalence. You see, now we are really using that we are mapping lambda k. Okay, so let us see what it means to say that this is a co-exact lambda equivalence. Okay, well, you check it out. If it means that this is a co-exact lambda equivalence, it means that for every diagram B from G to lambda K, you write the square of co-exactness, and here is what you get, softness. So you have a proof that lambda K is a soft category. Okay, conclusion. Whitman theory of free lattice can be extended to three bicomplete categories. Now, it can also be extended to bicomplete enriched categories, and also to bicomplete infinity categories. I wrote Lurie here in connection with the theory of finity categories. It's not the theorem of Lurie's, right? But, okay, that fits very well in Lurie's theory, and also in bicomplete enriched infinity categories. Okay, and the proof are all the same. The proof that I sketched to you, I'm not giving all the details, just work all the way through, everywhere. Now, it can also extend it to categories that are simultaneously closed under a class alpha of limits and a class beta. You don't need to be the same class. So, for example, we could take finite limits and maybe something else on the other side, whatever. And the alpha beta completion is alpha beta soft. So this is why I think the theory of bicompletions could be a fundamental aspect of general category theory. Now, there are applications to linear logic that were discovered with my work with Hongde Hu almost 25 years ago. And this is an aspect of this theory which probably needs to be further developed because it may give us a way of understanding combinatorially how to construct these three bicompletions. Because at least in the case where you want to complete just under product and co-product, it essentially works. I say essentially because there is also questions of pointed category, etc. So in the paper with Hongde Hu, we prove that the free bicompletion can be constructed using coherent space of Girard in the case where we only complete under product and coproduct, and in the case where we consider pointed categories enriched over the symmetric monomial pointed spaces. And so there is a lot to, to, to do there. Unfortunately, I stopped working on this and Hongda also 25 years ago. And but it's all to be yeah. So the references, uh, it would be thank you for your attention and sorry for the long.
Not at
Yeah,
all. Thank you, Andre. Thank you so
thank you.
much. And yeah, I think you did a really good job summarizing 25 years of work in uh in a little bit more than an hour. And I think my favorite quote was what you said, to prove that something is true, you have to believe that it might be true. So that's my favorite.
Yes, absolutely.
Thank you for the
And
encouragement.
it, it's
Uh,
so painful to try to prove something you don't believe it's true.
good reminder for all of us. Okay, so now we're going to question time. So if you're on the Zoom chat, there are two ways you can do this. You can either raise your hand and I'll call on you to unmute yourself, or you can ask your question in the meeting chat. And but before we go into questions, I just want to say that here on the Topos Colloquium, we sometimes go over time, and that's because we have recordings, and so people who are not able to listen to the whole talk and come back and catch up later. And I really encourage people to also ask questions via email if you're not able to stay on for the question time after the talk. Okay, I first want to read two comments in this that's in the meeting chat before we go to questions. First is Nathaniel, and he said that he was looking for the original reference to the characterization of the category of pre-sheaves as the one that uh preserves sorry, was it preserving limits? Uh, and the earliest reference that he found was Ulmer's properties of dense and relative adjoint functors. Okay. So oh,
Hulmer.
sorry. Thank you, Nathaniel. The defining property
Yes,
for
Hulmer. Yeah,
thank you.
Gabriel and Hulmer. Is it?
Ulmer's properties of dense and relative adjoint functors.
That's
That's
right. Gabriel
Oh, oh.
Ulmer, yeah.
Ah, so there is an explicit paper where it is okay, uh, okay, uh, okay. Good to know. Thank you. Yes.
uh yeah, these are just
If you could send me the actual reference, I will be happy to refer to it in my paper. Yeah.
okay. Thank you, Nathaniel. He said that he can send a reference after the talk. Maybe Nathaniel could email that to um Andre. And the second comment, which I thought was very helpful, was that this is from Fausch, that the rigid model structures that was studied to a fair extent by Tholen and Poulter under the name of Quillen factorization systems. And he gave a link in the meeting chat if anyone's interested. Rigid, rigid.
You mean that the notions of rigid model structures already exist? Is that what?
They were studied by Tholen and Poulter under a different name, under the name of Quillen factorization systems.
The notion is called Quillen factorization system.
Yes.
Ah, okay, good. Yeah, yeah, I should know that. I should know that. I apologize to Tolan and who?
Poulter, if I said it right, P-U.
Okay, 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 okay. I'm
Uh,
going to put it as a reference, right?
I thought that might be helpful for everyone.
Okay.
Okay, so we have two hands up. So Kevin, maybe you'd like to unmute yourself.
Sure. Thanks so much for the very inspiring talk, Andre. So you proved really quite thoroughly that the free bicompletion must be soft. You didn't really say anything about why it actually exists, right? Could you say a few words? I guess probably I can get it just from some adjoint functor theorem for a small category, but I'm a little bit nervous with that kind of thing for a locally small category.
I'm not. Let me try to reformulate what I understood from your questions because my ears are not good, and my I have some kind of hearing aid, and I. Okay, so are you raising the questions of whether, uh, yeah, why is lambda k locally small when k is locally small? Something like this?
Yeah. Why does it exist, basically? Yeah.
Yeah, it's a very good question. Uh, yeah. So how do I know it? Let me tell you how I know it. It's because first you develop the theory of this bicompletion. You put a bound on the limit and the co-limit you're using. So you could say, I'm going to develop the theory of alpha complete and co-complete categories, where you'd only take limits and co-limits of diagrams that are, let's say, alpha small. Okay, and for that, it does it's not so too difficult, but it can be technically to show that lambda alpha k is again small. Okay, now you can develop the whole theory of that I described today for lambda alpha k. I mean, you can put an alpha there and it works, and you get a lot of information about um, what happened when you increase alpha. So what happened is that if you increase alpha to beta, the natural functor from lambda alpha k to lambda beta, let's say alpha to beta to lambda beta k, you prove that this is actually fully faithful. In other words, as you increase uh, from alpha to beta, the set between the objects do not increase. What is increasing is the number of objects. Okay? In lambda beta k has many more objects, but the stay the same. That may be a bit surprising, but it's a bit less surprising if you realize that the fact that the functor lambda itself from k to lambda k is fully faithful. So the fact that the functor lambda is fully faithful is a special case of what I just said. It's the case where uh, alpha, I would say, is empty. Okay, but in general, the canonical functor from lambda alpha to lambda beta is fully faithful. And now you let alpha move to anything, and you get the result that your category is locally small.
Yeah, makes great sense. Thanks very much.
Thank you, Kevin, for your question. Then we have Nathaniel. Nathaniel, I believe your hand is up. You may unmute yourself.
Thank you very much for a fascinating talk. This seems like a very natural question to ask, and seems to have some very beautiful structure arising from it. I want one question in particular, which is about the relationship to Isbell duality and maybe the Isbell envelope. because this is a construction that also arises in relationship to free completions and free co-completions, and in particular, bicomplete categories. And so I was wondering, is there some nice relationship between the free bicompletion of a category and, say, the Isbell envelope or something like this?
Uh, uh, mm, Isbell envelope. Is that what you're saying? My ears are very bad. Isbell?
Isbell, yes.
Yes, Isbell. Yes, okay. Good question. Uh, I I have not looked into it, so that's something to look at. I mean, it should be there's yeah. Any kind of completion here should have a place in this picture. Of course, you want to know what happened with other kind of completions, right? Yeah. So I don't know.
Okay, thank you.
Sorry.
Thank
So that's an open question. Maybe you will have you will be able to answer the questions. Uh, yeah, yourself for everyone. For everyone. I will be happy to hear the answer to the questions when you have it.
I'll keep
thank
it in
you.
mind.
Thank you, Nathaniel. And I think Priya, I see your hand. You can unmute yourself.
Thanks, Shove. Thank you, Andre, for the great talk. It's very clear and
Thank
I
you.
really liked it. So can you please tell me a few words about the connection between bicompletion and linear logic, how they are connected? How does it give a semantics for linear logic?
Well, yeah, well, it's about coherent spaces. Uh, yeah, linear logic is what maybe could be called a substructural logic. I don't know if this is the right name. I'm not an expert of linear logic, but it seems that what Girard discovered was that the classical logic is summing up something which is more basic and which we call linear logic. And in this linear logic, you have conjunctions and disjunctions, and or, but they do not necessarily satisfy the distributivity law. The distributive law between and why is that? It's because uh, uh, it's the logic of dialogues.
Mm.
And there is a lot. There is something I find it hard to explain. I see Andreas Blas here. Maybe he could explain it better than I can. Uh, but I'm very excited by the logic of dialogues. I think it's a great discovery. And this is like something which has existed maybe 2000 years ago already when the Greek discovered logic and discussion and things of the sort. So I would love to be able to answer your questions. So the thing I could say maybe is to look at the paper with Hongde Hu, where we give an interpretation of these bicompletions in terms of some constructions of linear logic, coherent spaces, things of the sort. And that may be helpful. I must say I don't not understand linear logic as I would like. It's still something for me to learn. But that's about all I can say at the moment. I'm sorry.
Thank you, Andre. That's very helpful. Thanks.
Thank you, Priya, for your question. And in fact, I see on YouTube, Todd Trimble, he was saying that he seems to recall that when Andre, you were giving a talk about this at the CT conference in 1995, you mentioned that the free bicompletion of a star autonomous category is again star autonomous, and this Priya might help you, Priya.
Oh yeah. 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 So and examples. Yeah. Okay. So for example, the three bicompletions of category with one object, lambda one. So if take the category K with one object. So it's a strange bicompletion because what can you do with one object? You have one object. Let's call it X. Now, okay, I have one object. Then I could take many copies of X and take a coproduct. Or maybe I could take many copies and take a product. Or maybe I could take a product of a coproduct, and I keep doing product and coproduct like that, and I get more and more objects. And this is somehow what linear logic is doing with N and O. And it turns out that lambda one is star autonomous. The free, because one, the category with one object is obviously star autonomous, but lambda one is star autonomous for. And I would love to understand how to construct the objects of lambda one. And this is what we do with Hongde Hu in the paper. We construct a small part of lambda one.
Great. Thank you.
Right. Thank you, Priya, again. We have two more hands. I think Andreas, I saw your hand. So perhaps you can unmute yourself, ask your question. Thank you.
I believe I'm unmuted.
Hi.
It's not actually a question, but since Andre suggested that I might have something to say about linear logic, I'll say something, I think, disjoint from what he already said. If one greatly simplifies what Andre was talking about today and say, suppose I don't want complete or co-complete, suppose I just want products and co-products. So a typical object in the free whatever will be a product of co-products of products of co-products, and some alternating thing like that. And alternating things like that turn out to be very closely related to games. You can think of two players whenever think of in sets. I have a product, somebody has to choose one of the factors. Then you have a co-product, co-product. The other player gets to choose one of the summands, and they alternate in this way. And the first good news about this analogy is that morphisms between objects of the free product co-product category turn out to be essentially strategies for a player in one of these, in the associated game. That's the good news. More good news is that the push-out diagram, the softness, looks very natural in this context. It essentially says that there's no real difference between, suppose I have a strategy. At some point, it may want me to make a move in this part of the game and another move in that part of the game, and I have to decide which. If I can make the one move and guarantee to myself what move I will make in the other when it comes time to do so, that's the same as making that move first and guaranteeing that I will make this move when it comes time to go to. So this is the gluing together that happens in a push-out. So all of that looks like good news. Bad news is that once you start making identifications between strategies this way, that these two things that should be obviously the same are really the same, it creates headaches. For example, if I consider two things that I could do at the moment as equivalent, then a reasonable strategy for the opponent, the other player, should not be distinguishing between these. It should respond the same way to these two options of this now, that later, or that now, this later. And as a result, the description of strategies becomes much more complicated. And as a result of that, I don't actually know a good way to describe strategies. Even in this simple case where you're only doing products and co-products, they clearly have something to do with games, but there's something complicated going on in the flow of information between the players. And okay, that's as much as I know. So I guess I will just stop talking there.
Oh, thank you, Andreas, because you describe it in a much better way than I could do. That's really a nice description of the problem of construction lambda one, for example, because yeah, exactly, yeah. But I'm still, how can I say? I hope, but it's not because I hope that it's going to be true, right? Sometimes I hope something is true and it turns out to be wrong. So, but I hope that we may find some combinatorial way to represent these situations. But we have to work on it to find out because maybe there is some non-trivial step that has to be cleared out. It could be that somehow, yeah. So I hope that maybe we could find a way to describe these complicated, apparently complicated strategies. Yeah.
Maybe I should make a comment about hoping and what you said earlier about believing it's true before you can prove it. In many cases, the best way to believe something is true is to look for a counterexample and fail badly. Because it's often happened,
Yes.
But this is too good to be true. Let's find out where it goes wrong. And I can't find any place where it goes wrong. And then I start to believe.
Exactly. Yes, exactly. But that's related to your game theoretic description of logic, right? Because that's fine. It's like imagining some opponent. You imagine that maybe someone is going to question what you believe is true and come with some counterexample. So you put yourself in the role of the opponent, right? For a while.
Let's say I don't remember which role I was.
Ah,
I think it's symmetry there. I don't worry who's
yes.
who.
Thank you. Thank you so much. Thank you, Andreas. Thank you, Andre. I think we have time for one more question. So Nathaniel, I see that you have another question, so maybe you can unmute and ask your question.
Thank you. I have a lot of questions, so if I can ask just one more, I'd be very grateful, because I think this is a very fascinating topic. I was wondering, well, so in the case of free co-completions or free completions, we can characterize when a functor exhibits a free co-completion under some class of co-limits using something like fully faithfulness, density, and maybe some other condition about can extensions. I'm wondering, is there some sort of characterization of functors which exhibit bicompletions in terms of full faithfulness and something that works a bit like density or co-density, but is appropriate for bicompletions rather than co-completions?
My ears are very bad, and I think I was not able to actually grasp understand your questions. So, are you somehow suggesting what should be the constructions of lambda k or something like this?
Maybe I can type the question instead, or maybe I'll send you an email afterwards, and that will be easier.
Because my problem is with my ears. I mean, yeah.
I'll leave my question for now then. Thank you.
If you could send me your questions, send me an email with your questions. I will be happy to reply. Yeah. Thank you.
Thank you.
Thank you. Thank you so much. Thank you, Nathaniel. And let us thank Andre again for the really amazing talk today and for the discussion. Okay.
Thank you for everyone. Thank you. Thank you.
Thank you, Andre. We're going to end the YouTube live stream now, and we will continue in the Zoom chat. Thank you.
Okay. Yes. Good.
Okay, so the live stream is over.